Hello, welcome to this lesson of our study of differential equations. Okay, so we've been having lessons on how to solve differential equations, and particularly in first order. Okay, so if you have not subscribed to the channel, kindly subscribe to support the channel. Okay, so in this particular lesson we'll just go through how to solve a first order differential equation with linear coefficients. Okay, so you should always remember that when I talk about coefficient, then I mean that a first order differential equation written in the differential form, okay, like this. And then if these coefficients m of xy and n of xy are linear, okay, then we can say that they look like this. Okay, a1x plus b1y plus c1, then all dx, then a2x, like that. Okay, if this is true, like if you don't have any square term or any cubic term or anything like ln of x or something like that, and we have a linear form like this for both m of xy and n of xy, then we have two cases we have to consider. Okay, now how to solve them? In the first case, we'll have to do some transformation that will convert this linear coefficients to a homogeneous form. Then we use our idea on or in the homogeneous way to solve this. Okay, and I hope you've watched the video or the lesson on how to solve homogeneous linear first order differential equation. Okay, so the case one is, if you pick these coefficients, okay, when you come back to these a1, a2, okay, these ones, and then b1, b2, okay, if you pick them, and then the ratio of a2 over a1 and b2 over b1 are not equal, okay, if that is the first case. So case one, when these two are not equal, then we use the transformation below. Okay, so we transform this whole differential equation by saying that our original x should be equal to some capital S plus h, and our original y should be equal to some capital tau plus k. And then these k, okay, this k and the h are being found from the solution to this simultaneous equation. Okay, when we solve this, the values of x and y we get for this system, I mean the x and y you get here for the system of this how do I call it, linear equation. Okay, when you solve this, then we put x value to be equal to h and our y value to be equal to k, and then we come and put them here. Okay, so we'll get our original x being transformed to some capital S plus some k, and this k will be the solution we get for x in the system we're talking about. Okay, I know it looks plenty, but let's go through it together. Okay, and then the k will be the solution we get for the y in the system of the linear equation. Okay, so every point or every term here is really, really important, so that we'll be able to solve our linear ODE, I mean the first order, with a very easy way. Okay, now let's go to what will happen. So we are saying that our x should be equal to this, okay, and our y should be equal to this. Now from here, if I find the x, okay, the s will be equal to the x should be equal to ds, and then the y should be equal to d tau. I hope you get this. Now let's try to substitute these whole transformation back in the equation and see what will happen. When I put x is equal to some capital S plus h, so I put it here, and then y is equal to some capital tau or some tau plus k, then plus our c1, then ds. Okay, and since we said that dx is equal to ds, just put that there. Okay, and we still maintain our a1s and b1s and the rest. Okay, they are still there. So wherever you see x and y, you substitute these transformations in, and realize that when I expand this side of the equation, I'll have a1s plus b1 tau plus a1h b1k plus c1. Okay, and all times the s, and a2s plus b2 tau plus a2h plus b2k plus c2 times tau equals 0. Okay, so I hope you can understand this expansion. After expanding everything, look at this side. Okay, let me first erase the red marks. Okay, and then I will underline some points for you. Now look at these ones. What can you say about this side, and what can you say about A2H B2K plus C2? Okay, what can you say? Now let's go back to our system of linear equations. Okay, we said that this H and K are the solution we get for X and Y in this system. Okay, so if I know my X and I know my Y and I put them here, it will be A1H plus B1K. Okay, and we are saying that once you have the solution and you substitute them here, you add it to C1, you have to get 0. So it means that wherever I see A1H plus B1K plus C1, it should be equal to 0. And also, when you come back to the A2, the same H and K for Y and X. Okay, it means A2H plus B2K plus C2 should be equal to 0, since H and K are the solution to the system. Okay, so we are saying that we should find some solutions. We are trying to find X and Y values. When we put them here and add it to C1, we get 0. And then when we put them here too and add it to C2, we get 0. So once you know that the solutions are H and K, when you put them here, you have to get 0. I hope you understand my argument here. Okay, so it means that this whole point should go to 0, and this whole point should also go to 0. Okay, so let's go to the next one. So, but from the equations, okay, I even said it here. We said that these are the solution for this. So this implies that A1H plus B1K plus C1 is equal to 0, and also A2H plus B2K plus C2 equals 0. This simplifies everything to the homogeneous differential equation as this. Okay, so this everything will change to a homogeneous form like this, and this is indeed a homogeneous differential equation with degree of 1, because the variables we are dealing with here is s and tau. Okay, so if I find this will be m of x tau. Okay, this side, and this side will be n of s tau. And I hope you know how to find the degree of homogeneity and how to show that a differential equation, the first order, is homogeneous. Okay, so then we just use our idea in homogeneous to solve this. Very simple like that. Okay, let's look at case 2. Then the case 2 is saying that if these ratio are the same and they are equal to a constant p, okay, then you use this single transformation that there's some z, or substitution that there's some z which is equal to a1x plus b1y, and that when you find dz, I hope you can find that is equal to this. Okay, that is total derivative, or you can actually find dz dx, and after that multiply through by dx, and you realize that dz is equal to this. Okay, now if I make dy the subject, I'll get dy to be equal to dz minus the a1 dx all over b1. Okay, now you should know that since from this square, the top one, a2 over a1 is equal to b2 over b1 and is equal to p, meaning that a2 over a1 is equal to p, and that a2 will be equal to pa1. Okay, similarly b2 will be equal to pb1. Now I come back to the equation, that is, this is a linear differential equation, first order. Come back and put our things in, because we are saying that, okay, we don't touch this, but we said a2 in this case, okay, in the case 2, a2 is equal to pa1. So a2 is equal to this pa1x, then b2 here is equal to pb1, then we put that here, so pb1y plus c2. So therefore we said that the transformation was x is equal to a1x plus b1y. So you put z there. Okay, z is equal to that rather. And then here too, we can factor p out from these two terms. Okay, so we factor p out, we have this, and that is also z. So everything, this whole differential equation changes to z plus c1 ds plus pz plus c2 dy, and this is equal to 0. So this is a very simple one, and this, after substituting the value for dy in terms of, we put dy in terms of dz and dx, then this will change to a separable differential equation, which will be very easier for us to solve. I hope you got everything. So let's pick an example and then go through it. So example, solve the differential equation x minus 2y plus 1 dx plus 4x minus 3y minus 6 dy. So here, look through this and realize that this is not homogeneous. This is not homogeneous, and because when you pick the m of xy and then n of xy, you can see that these actually do not have a factor lambda or something like that. We can factor lambda something out, and so it becomes difficult for us to solve. And so one way we can also solve this is using the idea of linearity here, and so we compare coefficients. So comparing this to this general one, you realize that a1 is equal to 1 in this question, and b1 is equal to -2, a2 is 4, b2 is -3. So you find the ratio a2 over a1 is 4 over 1, and that is giving me 4. And then b2 over b1 is giving -3 over -2, and that is 3 over 2. But this shows that the ratios a2 over a1 and b2 over b1 are not the same. Since they aren't the same, what we do is we go by the first case, and that is saying that we should substitute x be equal to capital S plus small h, then y be equal to some capital tau plus small k. And now our h and k is from solving this system. I mean the m of xy and then n of xy, solve them simultaneously. The values you get for both x and y will be your h and k. So you're converting everything. This is how the equation looks like. So you can point this on a calculator, or you can use any method that you know in solving simultaneous equations to solve this. After solving, you realize that x is equal to 3, y equals 2. This implies that our h is equal to 3 and our k is equal to 2 rather. So here is supposed to be k. So k. Now with this, it means that my x should transform to capital S plus h, meaning my h is 3 here, so I'll put it here, and my y is also equal to this. Very simple like that. And we said that after everything, the differential equation will be transformed into a1s plus b1 tau. Always remember this, a1s plus b1 tau, then all ds plus a2s plus b2 tau or d tau, and this should be equal to 0. So all you need is just this transformation and these ones, so that you just come back and do your substitutions at the end. So this implies that this one is homogeneous. If you compare the degree is homogeneity of a degree of 1. It's a homogeneous first order differential equation. Because your m's will just be in terms of s and tau. So m of lambda s lambda tau will give you lambda to the power 1 m of x tau again. So likewise, the n will also give you the same thing. So in solving the homogeneous differential equation, we transform this one. Always we transform the one at the last, or you can transform one of them with the equation or transformation tau equals sv. If that is the case, then it means that the tau will be equal to s dv plus v d tau, or v ds rather. Then again, we just go into the equation straight away and put everything here. So this means that we have s minus 2, then tau is sv, ds, then plus 4x minus 3 into sv, then the tau is s dv plus v ds. I hope you can see, and this is equal to 0. So I simplify everything and I have s minus 2 sv okay, ds, then plus I have, what do I have here? 4s minus 3sv, then s dv plus v ds. Okay, now this should be equal to, everything is equal to 0. Okay, so this will give me s minus 2sv ds plus s dv. Okay, so this multiply the first term, okay, and we'll have something like s into 4s minus 3sv, right? 4s, s into 4s minus 3sv, and this we have dv. Okay, then the other one will give us plus 4s minus 3sv, then the vds rather. Okay, so vds, and this should be equal to 0, everything like that. Okay, so let's try to factor s out from each of the terms. Okay, realize that the first term, we factor s out, you have s out, then let me see what will be left. S out from here, I'll be left with 1 minus 2v. Okay, so I'll have 1 minus 2v. I hope you understand this. Or is it plus? Let me see. 1 minus 2v rather. Okay, yes, let me see. Okay, all right, 1 minus 2v, then ds, right? And the other one is when we factor, already there is an s here. Okay, so let me factor s from this bracket again, and when it comes out, we multiply this s, I'll get s squared, right? Or you can see what I'm doing. So I have plus s squared out 4 minus 3v, 4 minus 3v, then this is what? dv, right? Okay, dv, then plus, let me factor s out from here, and you have s out 4 minus 3v, then v ds. Okay, so therefore this is equal to 0, so I can actually divide through by s, and this s will go. Okay, this s will go, but one of these s's will go, so the square will go like that. So let's actually combine the, how do you call it, the s components. Okay, so I have 4 minus 3v multiplying v ds here, and I have this ds here. So in effect, I'll get 1 minus 2v, then plus v into 4 minus 3v, right? Or ds. And then with this one, I'll have plus s into 4 minus 3v dv, and this is equal to 0, right? So quickly, let me expand this one and simplify. I have 1 minus 2v plus 4v minus 3v squared, 3v squared, and ds plus s into 4 minus 3v dv equals 0. The reason why I'm not multiplying this is I want to maintain the variables like that, because you have s multiplying some expression of v. Okay, alright, so this whole side will be simplified to 1 plus 2v minus 3v squared. Okay, then the s plus s into 4 minus 3v dv equals 0. Okay, now I realize that when I divide through by this 1 plus 2v minus 3v squared, divide here by 1 plus 2v minus 3v squared. Okay, so this can take this out, and I'll be left with ds plus s into, okay, let me actually go and write it at a different page. Okay, so we have ds plus s into, the numerator is this 4 minus 3v over 1 plus 2v minus 3v squared dv should be equal to 0. And now we'll have to again divide through by s. Okay, when I divide through by s, what do I have? I have this whole thing. Let me multiply by 1 over s. Okay, so 1 over s here times the s, and plus, when I multiply 1 over s by here, okay, 1 over s, this s will take this s away, and so in effect I have only v here. V components 4 minus 3v over 1 plus 2v minus 3v squared dv, and this should be equal to 0. Okay, so if I take this one to the right side of the equation, I have 1 over s ds, and this should be equal to 3v minus 4, because I'll get negative of that, and when it affects, you have 3v minus 4 rather. Okay, plus 2v minus 3v squared dv. Okay, so therefore, if I even put whatever that is at the right back to the left and put the left to the right, it's still the same thing. Okay, so in effect, I have 3v minus 4. I would have done this, but I didn't want to confuse you. That is why I always try to do it like that. Minus 3v squared dv should be equal to 1 over s ds. And now you can integrate with method of separation. Okay, we've been able to separate this. So if I integrate this side, 3v minus 4 over 1 plus 2v minus 3v squared dv, and this should be called integral from this 1 over s ds. And know that this integral is the same as 3v minus 4 over, when I factorize the denominator, I'll get v minus 1, I have 3v plus 1. Okay, then dv should be equal to ln of x plus a constant c. Okay, know that we are left with integrating this one, and to integrate that, we have to convert to partial fractions. Okay, once we've been able to factorize the denominator, we can also convert it to partial fractions. Okay, and now converting it to partial fractions will give us this. I'm coming to quote it, and then I will urge you to actually go through that. Okay, go through that partial fraction, and then we'll get our a to be negative. Okay, let me write this. This is the same as integral a over v minus 1, because if I convert this to partial fraction, this is what I will have. The fraction here will change to a over v minus 1 plus b over that. Okay, then dv. I hope you remember this. And now converting it to partial fractions will give us a to be negative 1 over 4. Okay, then over 4 v minus 1, then b to be 15 over 4. Okay, then 3v plus 1, or dv. Okay, and this is the same as saying putting negative 1 over 4 out. This is a constant, so I'm coming to integrate them term wise. So I have negative 1 over 4 out, integral of 1 over v minus 1 plus dv, then plus 15 over 4, integral of 1 over 3v plus 1 dv. So this is in effect the same as when you integrate this side. Okay, the first one, you get 1 minus 1 over 4 ln of v minus 1. Okay, so here you can use substitution. Please just go through that and you get it. Okay, other than that, will keep long. I hope you understand what I'm trying to say. Just for the first one, use u be equal to v minus 1. You realize that du is the same as dv. Okay, and then in effect, you get back the solution I've gotten, okay? And then with the second one, use u to be equal to 3v plus 1. And then realize that dv is equal to du over 3. When you put it in, and then 1 over 3 will come and multiply 15 over 4, and you get 5 over 4 ln of 3v plus 1. I hope I've even gone through that with you, okay? So this is what you have for the other side of the equation. I mean this side, okay? The integration gave us this. So meaning that we have 5 over 4, okay? 5 over 4 ln of 3v plus 1, then minus 1 over 4 ln of v minus 1, okay, is equal to my ln of s. Then let me call my constant c. The constant was c, okay, so let's call it ln of a. So we realize we are saying that the ln of a is giving you c. So if I have a constant c and I'm saying that ln of a is equal to c, okay, ln of a is equal to, it means that my a is actually equal to e to the power c, and it doesn't change anything, okay? So ln of a is equal to c. They are still constants, okay? So this is 5. So I multiply through by 4 and realize that I have ln of 3v plus 1 minus ln of v minus 1 is equal to 4 ln of x, okay, plus 4 ln a, and that is still a constant, okay? And so I'm calling this whole constant, okay, let me call it, let me write 4 ln a, okay? Now I have ln of 3v plus 1 over v minus 1, okay, and this should be equal to ln of s to the power 4 plus ln of a to the power 4, and realize they are plus, so we can actually, from logarithm, we can multiply this and keep 1 ln, okay? So this is the same as writing s to the power 4a, meaning the ln, taking antilog of both sides, the lengths will go, there's a 5 here, sorry, multiply that and we'll get 5, okay? So this is actually equal to this to the power 5, okay? There should be a 5 here. I hope you understand this. This whole thing, when this 5 is gone, okay, when this 5 is gone, it means this whole thing will raise to the power 5 here, okay? It will raise to the power 5 here, and that will be it, okay? So this, I think this is cool. I hope you get this. So we have 3v plus 1 to the power 5 v minus 1, and it's equal to s to the power 4a. Now we go back to our question. What is our v? And we realize that we said that tau is equal to vs, okay? Tau is equal to vs, meaning that my v is equal to tau over s, okay? And also from the expression we just had, 3v plus 1 over 5, to the power 5 v minus 1 equals s to the power 4, then our constant a to the power 4, let me call it, let's say, a constant k, because it's still a constant, or you can call it a constant k, or whatever you want to call it, okay? So let me call it c1 rather. And that this whole thing, I mean, I can multiply through by v minus 1, okay? And that we'll have this equals this time v minus 1, then c1, okay? We said that v is equal to tau over s, so I put my v in, and that is tau over s for you, plus 1 to the power 5 equals s to the power 4 tau over s minus 1, okay? So I just have to simplify this, okay? Now we'll get something like 3 okay, into 3 tau plus s all over s. When I simplify the one in this bracket, then to the power 5 is equal to s to the power 4. Sorry, there's a c1 here. Then tau minus s over s, then c1. So this s can take one of these s's out and you'll get s cubed. Okay, I'm simplifying them before coming to put everything in. So it will take one of the s, so this s will go and then take one of these s's and we'll have s cubed. Okay, now this over this side is the same as writing it as 3 tau plus s all to the power 5 over s to the power 5 equals s to the power 3 and tau minus s, then c1. This will give me 3 tau plus s to the power 5 being equal to, when I multiply it through, I have s to the power 8. Okay, then tau minus s, c1. I hope you get this. Now let's go back to our question and say, and write back our formula. We said tau was equal to the substitution we did, y minus 2. Okay, I hope you get this. We actually said that y is equal to, let me first write them back. We said y is equal to tau plus k, and that k was 2, so meaning that it's equal to tau plus 2. Okay, and that if I make tau the subject, I have tau being equal to y minus 2. I hope you get the point. So that is it. And also with the x, okay, with the s, tau is equal to y minus 2, and then with the s, we said x is equal to some s plus some small h, and then h was equal to 3, so I have s plus 3, meaning this s is equal to x minus 3. Okay, so the question was given in terms of x and y, so I have to come and put them back. So I have this s being equal to x minus 3. So the solution to this is into bracket 3 multiplying y minus 2 plus x minus 3 to the power 5 is equal to x minus 3 to the power 8, then tau, which is y minus 2 minus s. Okay, so y minus 2 minus s is what? X minus 3, and this will give me y minus x minus 5. Okay, so it wouldn't go there, that's why I just simplified. Okay, so it's y minus 2 minus, so it's y minus 2 like this, y minus 2 minus this s, and this s is x minus 3, so it becomes minus s plus 3. So then you have y minus x plus 1. Okay, I'm really sorry, I didn't see that. Okay, so this will give me y minus 2 plus 1. Okay, I hope you get the point. Then this is my c1 constant. That is the solution. Okay, very simple like that, although it's very lengthy, but I presume you'll be able to get it. Okay, so once you see that your ratios are not the same, you just use the substitution we did. Okay, so let's look at the second one, and this is very short. Okay, to determine the general solution of this differential equation. Okay, x plus 2y plus 3 dx plus 2x plus 4y minus 1 dy equals 0. So you have to compare this to the general one, that's the linear coefficients. Okay, and a1 is this, b1 is that, a2 is that, b2 is that. Okay, but you realize that the ratio of a2 over a1 is 2, and that's the same as b2 over b1, which is also 2, and that is p. Okay, so if you remember in the second case, we said that if that ratio they are the same and is equal to p, then what will happen? What will happen is that the transformation we should use is z should be equal to a1x plus b1y, and that a1 is 1, b1 is 2, so I have z to be equal to x plus 2y. Now from the idea, we said dz, just differentiate the whole of this to find the total derivative, dz dx, or you can actually find the total derivative if you understand calculus of several variables, or you just find dz dx and that will give you the ZDS will give you here will give me 1. Okay, I'm actually differentiating the whole of this with respect to x. I have 1 plus 2 dy ds. Okay, because y is a function of s. So when I multiply through by x, when I multiply through by dx, so I have something like dz, okay, dx, it will be equal to this. Okay, so when I multiply through by dx, I'll have dz equals ds plus 2 dy. I hope you understand this. So that is the idea from this, and that if I make dy the subject, I'll have dy being equal to this, dz minus ds all over 2. Okay, so we keep that. Now here we said that z is equal to, the transformation equation will be z plus c1 ds plus pz plus c2 dy. And here our c1, you go back to the equation and realize that this is your c1 here, so you come back to your c1 is 3, and then my c2 is negative 1 from this equation. Okay, so you put everything there and you have z plus 3ds, that's okay, and then you put dy to be equal to this. That is what you just did. Okay, so I have z plus 3 dx plus 2z minus 1, then dy is dz minus dx all over 2, and this is equal to 0. Okay, so multiply through by 2 and you have 2 into z plus 3, and that will be 2z plus 6 all dx, then plus 2z minus 1, because they are the same term, they are one term. Okay, so when I multiply 2 through, the 2 would only affect this term. Okay, so this dz minus dx, minus 2, is it dz minus ds? Yes. Okay, all right, so equals 0. So if I expand the other term, I have 2z plus 6 dx plus 2z minus 1 dz, then 2z minus 1 into negative dx. Okay, and this is equal to 0. I hope you get this. So negative ds like that. So I have 2z plus 6 dx, okay, plus 2z minus 1 dz, then minus 2z minus 1 dx, and this is equal to 0 because of the negative ds. Okay, so when you combine the ds components, you have 2z plus 6 minus 2 minus into bracket minus of this, and so that will be minus into bracket 2z minus 1, then dx plus 2z minus 1 dz equals 0, and that will have something like 2z minus 2z again, okay, minus 2z again, then plus 1, was it? Yes, plus let me erase this and write it back. Okay, it's actually 2z plus 6, so 2z plus 6 minus 2z plus 1, then dx plus 2z minus 1 dz equals 0, and so that this will take this out. So I have 7 dx plus 2z minus 1 dz equals 0. So if I take the 7 to the other side of the equation, I have 2z minus 1 dz should be equal to minus 7 ds. So I integrate both sides, right? This is very simple. I think this is the cheapest integration you've ever gotten. Okay, so this is very cool. Then we go, okay, integral of that, and this will give me, this will imply that we have 2 over 2 z squared. Okay, I hope you know how to integrate. Then z equals minus 7x plus a constant c. Okay, so this will take this out. So I have z squared minus z equals minus 7x plus c. Now we know that the transformation we used was z equals a1x plus b1y, and that was x plus 2y. So you put it here, and you have x plus 2y squared, okay, minus x plus 2y is equal to minus 7x plus c, and this is our solution. Or you can simply rewrite it as minus 7. When you put minus 7 to the other side, you have 7x minus x plus 2y, okay, plus x plus 2y squared, and this should be equal to c. And I think this is an equation of an ellipse or so, something like that. Okay, so I hope you understood everything. Thank you, and don't forget to subscribe to my channel if you have not subscribed yet. Share my video, like, and also comment. Okay, unfortunately in this lesson I don't have a trial question for you. Okay, so I hope you can go back and then go through the questions yourself. Okay, see you next time.